Okay, so last class we were discussing about self and separate control of synchronous motor. So we will discuss some more same thing that using some other methods, like we have seen in even in the induction motor also there are different methods are there how to control this synchronous motor. Okay, so now we will draw. So load commutated inverter fed synchronous motor drive. So load commutator inverter fed synchronous motor drive. That is the next topic. So now you see here. So first I will draw the block diagram. I will draw the circuit diagram first. So you have, this is the output. Now this is a three-phase AC. So load commutator inverter, in the sense you have two converters here. You call this as source side converter. It converts AC to DC. Now assume that the voltage here is VDS, source side converter, and this inductor, you know very well what is the purpose of this inductor. We maintain this current almost constant, so ID current, whereas this voltage is VDL. Okay, so now this is load side converter. Then the supply goes to the synchronous motor. The current here is IS, synchronous motor current. Okay, so now remember this kind of circuit diagram already we have studied, that this load side commutator we will operate at a firing angle greater than 90. So if you operate at a firing angle greater than 90, what do you find out? This becomes minus, this becomes plus. I hope you remember all these things. We have been studying this one, that you have two full converters. In between that you have an inductor. So one full converter will act as a rectifier, another will act as inverter. So this is the case even in the induction motor also we have studied. The same case even for the synchronous motor also will do. But what is the difference here is that the stator, the armature supply will give from this one, whereas whereas uh, whereas this uh, field is given from your DC. Okay, this you know. I hope you know this thing. for the synchronous motor. Okay. Then what is the yeah? If anyone have a doubt, you can ask. Is it visible, audible clearly?
Yes, sir.
Okay, okay. Now you see,
Yes, sir, audible, sir.
yeah, okay. So what you need to understand here is that few things you need to understand here. What are the things is that this kind of structure we have already discussed in case of the induction motor. So I don't want to explain the operation of this entire converter once again here. But which is necessary, whichever is necessary, I will just draw that. Now you recall what is the phase current we got in those cases. Just recall that this is pi, this is 2 pi. So if you recall that the phase that is is, we are drawing is. So what is is you got there? If you have remember, so you got the pulse waveforms. You got the pulses. The duration is 120. This you know. Okay, something like this. Okay, so what is the duration of this 120-degree duration? What is the height of this ID? ID is the height of this. Okay, so this is the waveform of IS. So one phase current is this one. Okay, I hope you know this thing that how we got this also. We might have got even in the power electronics course itself, or even in this case also. Okay, so now what is the fundamental? Now this has harmonics. It is no doubt in this. This has harmonics because it is a non-sinusoidal waveform. So as it is non-sinusoidal waveform, okay, so this has harmonics. So if it has harmonics, along with the fundamental component, it has harmonics also. Okay, so now I will write what is the value of this fundamental component. Is it apply the Fourier series? When you apply the Fourier series, then you will get yourself what is its value. Okay, what is its fundamental component value? I will write here fundamental of is. What is the fundamental component of is? You got the formula. Now this formula you can derive using the Fourier series analysis. Okay, for the square. Now this is 120 degrees and this height is id. Okay, likewise you can derive. There is no problem in this. Okay, so this is the thing you will get. Now one more thing, I hope you remember this. What is the, for example, this firing angle is alpha 1, this firing angle is alpha 2. Then what is the relationship between alpha 1 and alpha 2? I hope you remember this relationship also. Alpha 1 plus alpha 2 is equal to 180 degrees. This also you know. Okay, and you got this relationship. Okay. We may require this relationship somewhere while solving any numerical problem. Okay, so this is about the load commutator inverter fed synchronous motor drive. That how do you do that? Is that what is the logic here? Simple logic. So first of all, I hope you remember this thing that how you control the synchronous motor. We have seen in the last class itself that how you control that the synchronous motor. Okay, so we will do one thing that we will draw a block diagram and I will explain further more. Means the same. This is the load commutator inverter fed synchronous motor drive. This is only power circuit I have drawn. Now I will draw the complete block diagram so that we can have the explanation here how it works actually. Okay, so now you see. Okay, so here we give the names now. This is three-phase supply, three-phase AC. This is source side converter, whereas this is load side converter. Now you remember between the load side converter and source side converter, you have an inductor. Okay, this is an inductor. Now the current here flowing is ID. Inductance value is LD. Okay, now this load side converter directly goes to the stator, or we cannot say stator here, so we should not. We'll say that armature. It goes to the armature of the synchronous motor. So this is your synchronous motor. Okay, and then yeah, this is the power circuit. This is the power circuit. So this is the power circuit. So just yeah, please answer. Is the screen visible to everyone?
Yes, sir.
Yeah, somewhere this we got disconnected with that. Okay, so okay then so we'll see now. What do you find out here is that current controller and firing circuit. Here also you have firing circuit because you have two converters. So obviously, okay, this is phase delay. ID, then this is current limiter, speed control. Okay, then we have this The terminal voltage. Okay. So now you see here, I will explain this thing that, yeah, one thing before I explain, I will tell you that, see, you have two converters, just like I have explained this thing that you have two converters. This is source side converter, this is load side converter. Okay. So we have seen the closed path. Now, what is the requirement here? What is the main requirement here we need here? What is the main requirement we need here? The requirement is that, see, both the converters are, they are having thyristor, so we need some firing angle for the thyristor. So assume the firing angle for the source side is alpha, whereas for the load side is beta. Now I hope you know this relationship between alpha and beta. Alpha plus beta is equal 180. So by following this we have to go ahead. Okay, this acts as a rectifier, whereas this acts as an inverter. This is the only way it is left now. So now how you are getting this alpha here? First you sense the speed here. So you are sensing the voltage here. You are sensing the terminal voltage. Terminal voltage in the sense the voltage that is going from the load side converter. So that voltage has some frequency, and also it has some phase angle also it has some. So this terminal voltage sensor will sense all these things, that what is the frequency of that, what is the magnitude of that, what is the phase of that, everything it will sense. So those signals, okay, we will take here as the feedback. Now another feedback is here. What is another feedback is here is that the speed of the motor. So either you can sense from here, either you can sense here. This is option. Directly you use your tachometer and I sense here. Otherwise you can do one thing. So from this terminal voltage sensing, you know the frequency, of that. So from the frequency, you know very well the speed is equal to 120 f by p. I hope you know this in case of the synchronous motor. So by sensing this terminal voltage, there you get the frequency. From the frequency itself, you calculate and you sense the voltage. You sense the means from the frequency itself, you calculate and you take this speed signal here. This is omega m is the speed of the uh, synchronous motor. Omega either you take here or you take like this. There is no. It's better you take like this through the terminal voltage sensor only, because you don't need an extra sensor here. Otherwise, you need a speed sensor here. So we don't need the speed sensor here. Directly we take from the terminal voltage sensor. There we know the frequency. So from the frequency we know very well. We calculate like this for the synchronous machine case. Then that speed will be sensed here. Okay. Now this is the reference speed of the motor. This is the reference speed of the motor, whereas this is the actual speed of the motor. So both will be compared here. Then the error is taking two path. One path is taking this here, whereas the other path is taking this side. So if you take this side, then based upon this error in the speed, so speed controller will be there. Then based upon that speed controller, okay, you will have another current limiter is there, because you need to limit the current here. Okay, based on how do you limit the current here? Once again you take this V by F control there. So by following the V by F control, what exactly you do there is there. So you will decide what is the current, maximum current it allows. So based upon that you have this current limiter. So current limiter. So based upon the error, based upon the error, speed controller will give a signal. So based upon that signal, now what exactly you do is that you need to control the current here. So otherwise, you know, it draws a lot of current, and so that problem is there. So the current limiter output will be here. Then that current, so you can say like this is the reference current. You can call it as reference current. Here you have reference current. You are getting the reference current here. So that reference current will be compared with the actual current. So you may have the current sensor here. So from the current sensor, you sense the current, what is the actual ID here flowing. So that will come here. Then there is an error. Then based upon the error, the current controller will produce the firing angle. So in another words, what you are here controlling, you are controlling the voltage here, VDS. You are controlling the voltage here. So how do you control the voltage here? With the help of alpha. How you will get alpha? Alpha you will get based upon the current signal here and the reference current. How you are getting the reference current? You are getting the reference current from the speed signal from the. So there is a relationship between all these variables. So that you can get from the basic equations of the synchronous motor. What is the relationship between speed and the current and the alpha? This you may get from the equations which we did not bring here. Okay, so now this you will get. Now coming to the other side, the speed error goes here. Then there is a block here. What is the sign of this error? So sign of this error in the sense maybe positive sign or negative sign. If you have positive sign, it means the actual speed is less than the reference speed. If you have negative sign, it means the actual speed is more than the. It's simple, something like this. Omega star, okay, minus omega m. This is the error. Now, when this error will be negative, when omega m is greater than the reference. When this is positive, when it is, when the reference is greater than omega. Okay, or your actual speed is less than the reference speed. So based upon that, you will have this firing angle beta. Based upon that, you will have firing angle. In the sense, see here, very simple thing that. So frequency, once again here, actual frequency you will sense what is the frequency here because you need a frequency. By changing the frequency only, you change the speed here. Okay. So and the phase angle of the terminal voltage also you require here. There is a relationship between frequency and phase of the terminal voltage also. Okay. So and then based upon that you have phase delay. I told you already what is the purpose of the phase delay, that you don't want this signal to be a sudden value, but you delay that, something like this. You recall, you delay it, not the abrupt change, you just delay it. So then based upon that, the beta value, so beta value depends upon what? Beta value depends upon this sign of the error. Why sign of the error? So that the controller will understand whether the actual speed is more than the reference speed or not. If it is more than the reference speed, what should be the firing angle? If it is less than the reference speed, what should be so this will be decided here. Then you will have the frequency also, you record the frequency also. So you will sense the frequency here from the terminal voltage sensor. Okay? All these including, you will generate beta. So generate alpha, generate beta, then the same procedure. Once again the speed will be sensed. So this is the closed path, complete closed path here. Okay, this is the closed loop control of this load commutator inverter fed synchronous motor. Okay, so then we'll do one thing, that we'll solve a numerical problem. So as of now, what we did is studied now. This is the power circuit of this load commutator inverter fed synchronous motor drive. Now I told you already, this power circuit is very same as your induction motor. Okay, how do you there also you got the similar kind of circuit diagram, but where is the difference is that this feedback path is different. Why the feedback path is different is that the control of the induction motor is not same as the control of synchronous motor. So there the parameters are different and here the parameters are different. So based upon those parameters, your feedback circuit will change. Okay, so it's better that you can compare this closed loop control of the synchronous motor with the closed loop control of the induction motor. There you will see the differences how we are controlling there. But the power circuit remains same because rectified power, then it is inverted power. So power circuit remains same. The controlling part is different. Now we'll solve a numerical problem. So I just want you to just go through this numerical problem. So this is about a synchronous motor. Okay. So the synchronous inverter, synchronous motor he has given. So then so what is the thing you need to understand here? A few things you must understand. So what is the data he has given? Based upon the data, we have to find out. Okay. So now you see now. A synchronous motor, a synchronous motor is controlled by a load commutator inverter, which is fed from a load commutator converter. See, sorry, line commutator. What is meant by line commutator converter, and what is meant by load commutator inverter here? This one, I think. Yeah, I have already drawn the circuit diagram, so better I will show the circuit diagram. See this now. Yeah, you can call this as converter, line commutated converter, whereas this you can call it as load commutator inverter. So that's what he said. So this is line commutated converter. This is load inverter. Okay. So now you see the question is that a synchronous motor is controlled by a load commutator inverter, which is fed from a line commutator converter. Okay. The source voltage is 6.6 kilovolt 50 hertz. So source voltage he has given. Load commutator inverter operates at a constant firing angle alpha 1 of 140 degrees. So now that's important. That he has given that what he has given, this is constant and this is fixed. So when he said it is fixed, so we cannot do anything else here now. So he said that this alpha or beta, whatever it is, of the load commutator inverter is how much? 140. Okay. So it is more than 90. So definitely for the converter, it is less than 90. We can say like this because we have that relationship previously also. Okay. So this is, you must understand, it remains constant, and when rectifying alpha 1 is equal to 0, it means the rectifier angle, the rectifier, because see, you have rectifier and inverter are there. So inverter angle he has given, what he said, load commutator inverter operates at a constant firing angle of 140, and when rectifying alpha 1 is equal to 0, DC link inductor resistance is this. So this data he has given, that at that time, what is the value of alpha? He said the value of alpha, he said, is that it is 0. Okay. So this data he has given, and what's next now? What's next he has given now? DC link inductor resistance is 0.2 ohm. So this value he has given, it is 0.2 ohm. This resistance value he has given. The drive operates in self control mode with constant V by F ratio. So this, we constant V by F ratio. I hope you remember this thing. The motor has the following parameters. Okay, 10 megawatt. Okay, so these are the ratings. Okay. Okay, these are the ratings of the motor, whereas these are the source voltage. This is the source voltage, three-phase source voltage, whereas these are the ratings. 10 megawatt, three-phase, 6000 volts, 6 poles, 50 hertz, unity power factor. So he has given unity power factor. Okay, star connected, unity power factor, star connected, and synchronous reactance he has given. And similarly, he said RS is 0 in the sense that resistance value is 0. Okay, then what you have to find out, determine the source side converter firing angle. So you have to find out the rectifier firing angle, for which case, for motor operation at a rated current and all these things. Okay. Okay, so at the end, what you have to find out, the question you need to find out here is, you have to find out the source side converter firing angle. So something data he has given. So always it's better that we start with the question. The question is that you have to find out the source side firing angle. Then how do we proceed here is that, now first of all, where can we find out this angle alpha? Okay, somewhere we need some equation, one equation we need, so that we can find out the alpha there. So I will tell you one equation which relates the rectifier firing angle. So now the rectifier is the control rectifier. So as it is a control rectifier, so for the control rectifier, what is the output voltage equation? VDS. VDS is the output voltage of the control rectifier. Which one? You see here, this one. Yeah, this one, VDS. So output of a control rectifier. So three-phase rectifier. So we have got this already in the previous classes itself. So I will write down that equation 3 root 6 by 5. Okay. Phase voltage. Okay. Cos alpha. I will write yes here so that the source here also I will write yes. It's the source side. Okay. We will use this equation. So in this equation, what we require here? What we require here? We need to find out alpha s. So from this equation, I will write one thing. What is alpha s? Alpha s is equal to cos inverse of cos inverse of. So VDS into pi whole divided by 3 root 6 into V phase s. So this is the formula you will get from this. Now we will search one by one. What are the things we know? Okay. First thing is that. First thing is that. So first thing is that only two unknowns are there here. Nothing else is there. One is VDS, the other is V phase. So we definitely need to know about these two. So what is V? We can easily find out V phase source. How can we find out? The line voltage he has given in the problem somewhere. Okay. What is the line voltage he has given? Line voltage in the sense source voltage. 6.6 kilovolt. That's the line voltage. So what is the phase voltage then? 6.6 kilovolt divided by root 3. This is the answer you will get. Okay, some answer you will get. We'll put like that. Then VDS, we don't know. How do we find out VDS here? So let me go to the circuit diagram. Yeah, this VDS we need to find out. Yeah, how to find out VDS? So what is the procedure to find out VDS? Then we have one relationship. We can apply KVL here. We can apply KVL. We search all these things. Then we need to find out the alpha here. That's the thing what we are doing now. So you will apply KVL here. So if you apply KVL, this is plus minus, this is minus plus. So what is the answer you will get here if I apply KVL here? So we'll write the KVL equation here. What is the KVL equation? VDS plus VDL is equal to ID into, now he has given some resistance of this inductor, so that resistance I will put here RD. Yeah, this is the KVL equation. See, why I did not include LD here? The reason is that we already know that the purpose of LD is to maintain the current constant. So if you maintain the current constant, then LDI d by dt. What is the answer? You will get 0. Why? Because the current is constant, so the inductor voltage drop is 0. So then what is left there? Only resistance is left. So that resistance I put here. Actually, it will be IDRD plus L did by dt. But this L did by dt is equal to 0 because ID is constant. So we got this equation. VDS plus VDL is equal to IDRD. Okay. Then what's next now? What's next is now is that. So RD value he has given. Now, okay, we'll just bring this equation this side. VDS plus VDL is equal to IDRD. So we'll bring this equation here. VDS plus VDL is equal to IDRD. Now, what are the things we know and what are the things we don't know? Okay, see this now. Here RD value he has given in the problem. RD is equal to, somewhere he has given in the problem 0.2. 0.2. Okay, and then because what exactly we are trying now, we are trying to finding out VDS. So RD we know. Okay, and then we will find out ID. What is ID now? Question is now what is ID? I need to know what is ID. I need to know what is VDL. So these two things, if you know, then we can find out VDS. We substitute the VDS here, then that's it. We got the answer for alpha S. Okay, we got the answer for alpha S. Okay, now yeah, how do we proceed here is that, yeah, ID. How can I find out ID? Then we will recall any equations we know for ID. We will see that is there any equation we know for ID. Somewhere we may have, yeah, one equation we know here. Please see this equation. So we will only search the equations which are suitable here. Then using those equations, we will just do something. So what is that equation we got for IS? We got IS equation. IS is equal to root 6 by pi ID. Yeah, from this we can find out ID. What is ID? ID is equal IS into pi by root 6. Okay. So we have a clue here to find out ID. Once again, to find out ID, what I require? I require IS. What is IS? We'll just go to the circuit diagram. Everything is simple here. That you see, if you know the equations, it is very simple to solve. Here is IS. Yes. So we need to know this IS value. How to find out this IS value? What is the procedure to find out this IS value? Okay, what is the procedure to find out IS value? So IS is the source current of stator current of the synchronous motor. And now the synchronous motor, what he has given, just see this now. Synchronous motor, he said star connected. One important data he has given, star connected. And the power factor is unity. So these are the, see, one thing we need to understand that these are the rated values. These are the rated values. Now you see the question, what is the question he is asking? So he said that converter firing angle for the following motor operation at rated current. He has given this data. This is important data. Rated current. And the speed is 500 RPM. So the current is rated. This is very important. So which current it is? Rated current of the motor. So now the motor data he has given rated values. Then from this we will find out the rated current. So that current is nothing but IS here in the problem. That current is nothing but IS here in the problem. Okay. IS. So IS here, now in this particular problem, IS here is the rated current. Okay, IS is the rated current because the question is rated current. Which rated current? Rated current of synchronous motor. That's important. So IS is the rated current of synchronous motor. Now to find out ID, I need to find out the rated current of synchronous motor. How can I find out the rated current of synchronous motor? It can be finding out. It can be find out by knowing the rated values of the synchronous motor. Yeah, that is the only logic it is left now. So then we will copy these rated values. So we have got a clue here that we need rated values to understand this. Okay. Now you see rated power he has given, rated voltage he has given. Okay. And then what else we require here? So now first of all, power is given, voltage is given, then you can easily find out the current. What is the formula? Power is equal 3 V phase I phase, 3 V phase I phase cos theta is the formula. So power is 10 megawatt. So 10 megawatt is 10 into 10 power 6 is equal to 3 into V phase. How do you find out V phase? See this now. So we'll see now. See rated power he has given and he has given the voltage also. Yeah, please, there is a small correction in the voltage. It's not 6,000, 6,600. Please correct it yourself. It is 6,600. Okay. So there is a, well, take that. So 6,600. So rated voltage also he has given. So I will correct here also. It is 6,600. So now you see yourself. See yourself now. So 3810 and 5. So here, what is V phase here? It is star connected. So 6,600 by root 3 is the phase voltage. Into I phase. That is what we have to find out. I phase. Into cos theta. You will take here unity power factor. See this now. He said unity power factor. So cos theta is equal to 1. Rated values are like this. So then from where we can find out I phase. What is I phase value? You will get here. Okay. So into 3 into 3 inverse of that, then we multiply with yeah. So you multiply with 10. Okay, you 10 power minus 1 is 10 power 6. So this is 100. So you multiply with 100. Oh, sorry. Yeah. So 874.77. This is I phase is nothing but IS. It is nothing but IS because the IS is the current here. I said so that current we find out here. It is nothing but IS. Okay. So now that current will substitute here in place of ID. Okay. Then we got answer for ID. So we'll do one thing. ID. ID is equal to, what is the formula for ID? ID is equal to IS into pi by root 6. IS into pi by root 6. And then okay, once again root 6. Yeah, we got the answer 1122.13. 1122.13. So this is ID value. So we got ID. Now what else we require? Please see this now. Why do we require? We require ID. We know already RD. We want to find out VDS. That is the job here. So then what is left now? VDL is left now. How to find out VDL and where is VDL first of all? Where is VDL? So where is VDL is that? Here you have the VDL. Okay, so how to find out VDL? It is also a controlled rectifier. Please see this now. It is also a controlled rectifier. So in the controlled rectifier, okay, so as it is controlled rectifier, as it is controlled rectifier of what? Load commutator inverter. So this is the control, it is the load commutator inverter. So this VDL we have to find out. This is also a full converter. So what is the formula for the full converter? We will use the same formula which we have used for this first converter because both are full converter, but maybe firing angle is different. So I will write one more equation here for VDL. What is VDL equation now? VDL. VDL is equal to 3 root 6 by 5 into once again V phase into cos. Better I will write some other because here I have used theta already. Yeah, alpha yes I have. Yeah, I will write here alpha L load side. Okay. So then we will substitute this here 3 root 6 by pi into okay one by one we will find out here. To find out this, first of all, what you require is that what is this phase voltage now? This is the phase voltage. It's important. This is the phase voltage. Okay, so now you just go back your phase voltage. You will just go back here. What is the phase voltage you got? Eight. You got yeah. This voltage you got 6600 by root 3. This answer we got. Okay, but is this the phase voltage you will take here or not? The question is why it is so. So the reason is that we'll do one thing here. You know very well this phase voltage it depends on frequency. It depends upon frequency. So when it depends upon the frequency, then we need to know what is the frequency of the synchronous motor because this is the load side. This is the load side phase voltage you have to find out, not the source side. Source side is directly 6600 by root 3, but this is the load side you are finding out. Then you need some more data. Why you need some more data is that see what he said. What is the speed? He said the speed is 500 rpm. It's very important now. So you got the speed as 500 rpm. So if you have the speed as 500 rpm, then what should be the frequency? Because frequency and speed are related here. This you know very well. So we will use this one. We will use this one. Then n is equal to 120 f by p. So it is 500. So 500 is equal to 120 into f by p. Number of poles are 6, I think. Yeah, he has given 6. Yeah, 6 poles. And then what is the value of f now? F is equal 500 into 6 divided by 120. It's 25. So you got the answer here. Frequency in this case is 25 hertz. This is very, very important because we are now solving on the load side. So as we are solving on the load side, so what are the parameters on the load side that we need to understand? So why we need to understand here is that the parameters on the load side are different because the speed is 500 rpm. So corresponding frequency is 25 hertz. Okay. So the frequency here in this case is 25 hertz. Okay. Now, what is the phase voltage in that case? Because we know that we know this thing that the voltage depends upon the frequency. The voltage depends upon the frequency. Now, frequency now becomes 25 hertz. But we know the voltage is 6600 by root 3. It is for 50 hertz because you see the ratings of the induction motor. It is 50 hertz. See this now, 50 hertz. So for 50 hertz, this is the 6600 volt line voltage. So 6600 by root 3 is for 50 hertz. Then what is for 25 hertz? Then how do you find out the V phase for 25 hertz? To find out V phase for 25 hertz, simple thing. I hope you can do like this: 6600 by root 3. They are directly relationship. 25 by 50. So this is the V phase 25. 25. So that V phase we'll put here. Okay. So then I hope you understand why we are doing all these things, because the frequency is different. Your voltage depends upon the frequency. Why frequency is different? Different because the speed is different. Speed is not rated value. Okay. So because we are following V by F control. Please recall that we are following V by F control. In the V wave control, you know very well that when you are operating below the rated frequency, you maintain the V by F constant. If it is above the rated frequency, you maintain the voltage constant. This we know. So as it is below the rated frequency, why it is below the, because the speed is below the rated speed. That is 1000 by 1000 is the rated speed, but the actual speed we are operating is now 500. So it is lesser than the rated speed. So the frequency is reduced. So as the frequency is reduced, voltage also you have to reduce, because for below rated frequencies, you have to maintain V by F constant. To maintain V by F constant, if F is reduced, V also should be reduced. That is the reason that I am doing all these things. Then what is the answer you will get here? 6600 divided by 0.732 divided by 2. 1905 So this is the voltage. So this voltage you will substitute here now. 1905.3 into cos alpha. So cos of, now what is alpha of the load side? He has given in the problem. Just let me go back to the problem. Yeah, he has given somewhere. Yeah, load side combined inverter operates at a constant firing angle of 140. So this firing angle is constant, he said. Now it is 140. Okay, so 140. So you put here 140 cos 140. So why we are doing all these things? Because we want to know what is the value of VDL. Okay, then we'll find out into one thing. 140 cos of 140 is this. Then you multiply with 1905.3. You multiply with 3. You multiply with 1.414 into 1.732 divided by 5. 3413. So whatever the answer we got, we'll write directly. Minus 3413.39. So, but okay, we'll take only the magnitude because we have already included it in the equation. 3413.39. So this is VDL. Now we got the answer for VDL. Now we'll go to the actual equation. Now what is the actual equation? The actual equation here is yeah, this equation. We need this equation now. This equation we need. So we'll bring this equation here. So in this equation, we have to find out VDS. That's what is the job actually. So VDS is equal IDRD minus VDL. Then with this we got the answer minus here. So we got the answer minus here. Then ID value, how much we got just now? Somewhere we find out ID value. Yeah, 1122.13. Everything we find out now. Only into RD value 0.2. So minus of minus plus 3413.39. So this is VDS value. Okay, this is VDS value. So we got the answer for VDS now. Okay, 1122.3 into 0.2 plus 3413.39. 3637. Is 1.85. Okay, we got the answer 85. This is VDS. Now we got the answer for VDS. Now why we are doing all these things? Because you have one equation, first equation, very first equation, which we have started the problem, this equation, because we want to find out alpha s. So this is the best way that you always start with the question that what exactly you have to find out. Then you try to find out, okay, which parameters are missing and how to find out. Okay, we'll substitute this here now.
సార్
Yes, please.
టు మనము అక్కడ వీడి వాల్యూ నెగిటివ్ తీసుకున్నామా సార్?
VD value is positive. See here, I will show you the circuit diagram here. So you see the circuit diagram. Here we have taken minus plus. Okay.
ఎస్ సార్.
So generally, see, only logic is that I will tell you one logic here. What will be the ID value? This is okay. You take the convention plus minus, say for example, but you are getting a negative answer. So when you get a negative answer, then you put here, you get this equation: VDS plus VDL is equal to ID RD. Am I correct? This equation is correct. If I take this as the polarity,
ఎస్
minus
సార్.
plus.
ఎస్
Yes.
సార్.
Okay. So then with this polarity, what we did now, we are finding out now VDS from this. What is VDS now? IDRD minus VDL. Yes,
ఎస్
you
సార్.
get answer IDRD minus VDL. So when you get IDRD minus VDL, ID we have find out already. So then minus VDL it is. So now minus VDL in the sense, what is the answer you will get here? Now it depends upon what is the polarity you have taken. Nothing else is there. Okay.
So we got VDL as a negative value, sir. So we neglect that negative, or do we consider it in the equations?
Yeah, we will consider in that equation. No problem in that. Or else we'll check yourself. We got VDS more than VDL. See, we got two answers. VDL we got the answer. VDS we got the answer. See sometimes to avoid this confusion, we just I will tell you one thing that just take an assumption. You have two options. One option is that you put here minus or you put here plus. Am I correct? There is a confusion
Yes.
actually.
Yes,
Yes.
sir.
Okay. Yeah. For example, you put here minus. You put here minus. Then what is the answer you will get if you put here minus? I will just check this. 1122.3 into 0.2. Okay. Minus 3413.39. Okay. So you got 3188.93. So we can say this thing that from the circuit, see here, if you take that case, this voltage is lesser than this voltage. Am I correct or not?
Yes, sir.
So now the question is that practically is it possible that this voltage is lesser than this voltage?
No, it won't.
Just imagine yourself. I don't think so that it is possible because the source is on the left side. The source is this side. The source is this side. So obviously this voltage should be more than this because there is a drop is there here also. There is a drop is there and that too it is an inverter. So the power flow, okay, the power flow is like this. Am I correct now? You agree with me that the power flow is like this?
Yes, sir.
So if the power flow is like this, then we can easily say this simple logic that the left side part will have higher potential than the right side part. Am I correct now?
Yes, sir.
So I think we are doing the right thing. Okay. Yes. You
Okay,
understand
sir.
now?
Okay, sir. Yes, sir.
Okay. So then you see sometimes there is a problem with the mathematics that the mathematical notations and the actual our circuit notations or the real notations may be a little bit different. Okay. So here what is the answer? It is 6600 by root 3 because this we have already seen. Yeah, this we got already. Yeah, this one we face. Okay, source side, it is source side, not the load side. So then we solve this now. 3637.85 multiply with 5, we got this answer, divided by 3, then divided by root 3, root 2, 1.414 divided by 6600. See, you can cross check yourself, there is no problem in that. Okay, so we got 65.9, that's the answer. So 65.9, that's it, this is the answer. Okay, so I hope the time is already over, so it's exceeded. Okay, so